Hello, everyone. Welcome to the show. Today, we are joined by Professor Bob Scholes, I guess, Robert Scholes, and he's going to educate us about climate change for thinkers. Okay, thank you, and over to you, Prof.
Thank you very much, Hugo. To start off with, we should probably, I'm struggling to change slides here. I've got screen sharing on, but my slides are not advancing. What I'm going to have to do is probably to unshare the screen and then select again.
Okay, you can do that.
My slides aren't advancing is the problem. Okay, now how do I go about doing
I think unshare, share again, and then there's an option for share PowerPoint and share screen.
Oh, there we go. Stop share. Okay, share screen. I'm going to try that one. Share, and I'm going to go on to slideshow. All right, let's try again. Right, so to start off with, let's clarify some terminology here. What do we mean when we're talking about climate change? The climate of the world has never been stable, not at any time in its entire history. It's changed many times, and even when it's in periods of relative, when it's in a particular mode, there is variability from place to place and from time to time. So when we're talking about climate change, we're not talking about that. We're talking about anthropogenic climate change in the modern era, and we set that arbitrarily at starting somewhere around about 1750 when we started with the industrial era. And it is human caused. It's not caused by the internal dynamics of the climate system itself. The climate system is a complex non-linear system, and so like all such systems, it has different modes. And a very good example of that is the ice age, non-ice age variation that's occurred over the past 4 million years. There was a cold mode and a warm mode, and we oscillated between that with a time period of about 100,000 years. So that's not what we're talking about, and we can in fact exclude that as being a factor in our current situation, largely because of the timing. It's also not the variation which is caused by solar forcing. The best known solar forcing, of course, is the day-night cycle due to the rotation of the Earth. There's also a seasonal cycle due to the movement of the Earth's orbit around the sun. And there are a whole bunch of similar fluctuations, including the 11-year sunspot cycle and all kinds of other exotic things called precession and eccentricity, et cetera, We know about all those things, and they are factored into our calculations of how the climate changes, and they're not responsible for the changes we've measured over the past century or so. The third important thing is that when we talk about the climate systems, we're not just talking about the atmosphere. When you think climate, you think, oh, that's something that happens in the air. The climate system has 4 really important components, and they're equally important. It's the atmosphere, the oceans, which are the main store of climate energy in the world and the main way in which energy is transported between particularly the equator and the poles. The ice bodies, by which we don't mostly mean sea ice, that's a small fraction. We're mostly talking about large ice masses on land in Antarctica and in Greenland, but also including things like permafrost and glaciers, etc. And then finally, ecosystems on land, which are a major source of the carbon, which is an important part of the natural climate engine. And increasingly, when we talk about the climate system in the modern era, you have to include people, because it's the changes wrought by people which are moving the climate from its previous pre-1750 state into the current state it's in. And we're currently in a transient, we're not at any kind of equilibrium. And the other important point that people miss is that weather and climate are not the same thing. Climate is the average over time of weather, and we can talk about changes in all the statistical properties, changes in the mean. We can also talk about changes in the variation. you can't predict the weather more than about 2 weeks into the future. And that's because of the nonlinear nature of the climate system. You get mathematical bifurcations and sort of apparent chaos setting in at time periods larger than that. But like all such simple systems, by taking a probabilistic approach and integrating over long periods of time, you can predict climate. So when I say the climate in the year 2100 is going to be this, I'm not saying that 3 o'clock in the afternoon on a Saturday afternoon in October in 2100, it's going to be 32 degrees Celsius. I'm saying that in that integrated over time in that period, this is what the average weather is likely to be. And so we know what the key drivers of the contemporary climate change are, and there are two very important ones and a couple of minor ones. The main one is the increase in these things called greenhouse gases in the atmosphere, the concentration change in the atmosphere. And the second large one is changes that we've wrought on the land surface. So we've, as humans, over the past 200 years, transformed about 3/4 of the Earth's surface in substantive ways. Some of it radically, we've built cities, or we've substituted one ecosystem for another. In other things, we've just altered it to a degree, for instance, thinning out forests or overgrazing grasslands, etc. So let's talk a little bit about greenhouse gases. There are, all gases which are radiatively active. In other words, they interact with solar radiation passing through the landscape, through the atmosphere, are greenhouse gases. But there's three really important ones which together add up to about 90% of the effect. And then there's a whole string of other ones which contribute as well. So if we plot the amount of radiant energy on the y-axis against wavelength for a body such as an emitting body such as the sun. Now, the surface of the sun is at 5,250 degrees Celsius. The interior is much hotter than that. And so it emits its radiation according to the Stefan Boltzmann law, and it produces a hump-shaped curve that looks like that. And you can see that there are certain wavelengths along that hump-shaped curve where different gases are particularly effective at absorbing those wavelengths. And the reason that they are is because of their molecular structure. And that's why I've drawn those little molecular diagrams up there. It's in particularly those little bonds between the atoms. They vibrate at a certain wavelength, and that makes them strongly absorptive. And we've known this, in fact, since the middle part of the 19th century. And as a result of their different molecular properties, these different gases have different effectivenesses and different wavelengths at soaking up that radiation. But they also have different lifespans in the atmosphere. So something can be extremely efficient at absorbing a particular wavelength, but it might not last for very long in the atmosphere. So to understand its integrated effect, you have to work over both its absorptive capacity and its concentration and its lifespan. So why does this then result in the world warming up? Well, the reason is that solar radiation then warms the surface of the Earth, not only the land surface, but the oceanic surface. And the average surface of temperature of the surface of the Earth is 21 degrees Celsius. And so it re-radiates that energy according to the same fundamental theory as the sun is radiating, but because it's a much cooler surface, that radiation is shifted to the right. And there are a series of gases in that area more dominated to the right, particularly the infrared area, which are extremely efficient at absorbing that outgoing radiation and much less efficient at absorbing the incoming radiation. And the result is that when you change those concentrations of those gases, which are present in very, very small amounts, the most abundant of that is carbon dioxide, and it's only 0.03% of the atmosphere. But that small amount is enough to change the balance of incoming to outgoing radiation. And because now you've increased the amount, the outgoing is slightly less, and as a result, the temperature of the world warms up a little bit until a new equilibrium is struck, because the slightly warmer world will radiate more energy and a new balance is struck. So the important thing isn't the absolute concentration of those gases, but their change since the industrial period. Carbon dioxide's gone up by, close to 50%. Methane has gone up by 250%, and nitrous oxide by about 24%. So there's some interesting issues around why South Africa in particular is vulnerable to climate change, quite apart from social issues of our ability to adapt and cope. There are issues about our location. And these really tie into the circulation patterns in the atmosphere above us. And South Africa falls just at the junction of the Hadley cell, which is the sort of sausage-shaped circulation which rises at the equator and descends approximately at the Tropic of Capricorn, and the next circulation system, which is called the Ferrel cells. And because of that, and because you can only get an integer number of circulation systems in between the poles and the equator, as we warm the world up, those circulation systems intensify. And so we get a greater intensity of descending air over South Africa, which is descending air is always what brings us our clear skies and our bright sunshine and our high temperatures. Whoops, sorry, I went too far there, going back one. And so we have evidence of the mean surface temperatures over the whole world and over the oceans increasing over the period of record. And that period of record starts about 1850. The oldest records in South Africa are about 1850. And as the time goes on, you get more and more stations contributing to this. And you can see that that map of Africa, there's large areas which are not colored in because there's just not enough records there for us to say anything of certainty. But the places where there are colors, we have enough weather stations to do that. And you can see that the colors there are all in the kind of yellows and oranges and reds. So there's no place on land which is actually warming up, cooling down at the moment. Everywhere you see is warming up. If you look at the global records, the only place in the world that's actually cooling is a tiny spot just south of Greenland in the ocean. And that's because of increased overturning of the ocean in that as the oceanic currents struggle to cope with these changes in energy inputs. People who look at this data and say, but how do we believe that it's all massaged and fiddled with? If you think through what it would take to do that, it's completely impossible. I would have to sneak off down to the observatory in Cape Town and get out the old records, which from 1850 and alter them, and I'd have to do that in about 100,000 places around the world. You just can't kind of fake this data. And the processing which goes into making sure that you can build up the time series, yes, there's different approaches you can take there, but no matter which approach you take, you get this statistically significant increase in temperature over the 20th century and an ongoing increase in temperature. When we project these changes using climate models into the future, the important thing I want you to take away from this is that while the world as a whole, when you warm it up, actually gets wetter, and we know that from the paleo record, for instance, during those Pleistocene periods when the world was much colder, during the glacials, it was also drier. We saw expansion of deserts in that period. And when we warm the world up, it gets wetter. And the basic reason is you get more evaporation. And so there's more vapor in the atmosphere. What goes up has to come down. But because of our location in the descending limbs of the Hadley cells, we in fact get both warmer and drier. Okay, it's a little kind of feels unfair because it's hard to deal with that, but it's a consistent result that comes out. And if you look at those three world pictures, the top one is for the first part of the 21st century. Then you see middle of the century and end of the century. You see that the most of the world is the kind of in the bluish colors getting wetter, whereas the two bands around the Tropic of Capricorn and Cancer are the brownish colors getting drier, and that intensifies into the future. So those kind of global pictures are all very well, but they're quite hard to relate to. And even myself, you're feeding these numbers into a huge supercomputer, in fact, dozens of huge supercomputers, and it chunders away and you can't understand, all the things that are going on in there. So how can you really be sure that this is true? So I happen to live in a small town in Mpumalanga called Witwatersrand, which it's a very old town, founded in 1859. So we have a very long daily weather record for there. And I put one of my students onto typing in the daily weather record from Witwatersrand since 1904. That's what you have graduate students for. And we analyzed that record. And there's a very, very strong increase in temperature, particularly the nighttime temperatures over the period of record. We can also use these very sophisticated models, and we run them at the Global Change Institute at WITS. It's the only global climate model actually based in Africa. And we're able to do downscalings. We're able to actually work out the climate for particular points, not great big squares, distributed around the world, but for places like Witwatersrand. And here is a plot of such simulations showing the anomaly in rainfall. So on the x-axis, how much more or less rainfall. On the y-axis, the temperature anomaly, how much warmer or colder, into the future. And so the different colors are for different eras. So the bluey colors are for the present and the past. The orangey colors are for the sort of 2020s through to the 2080s, and the reddish colors are towards the end of the century. And so what you can see is, the enormous scatter of points. Okay, that's because there's variation within years, and between years in a climate era. There's also great variation between the predictions of different models, but the overall pattern is very clear that we have moved up in 2015. We're quite a long way from that crosshair, which is the kind of normalization time. And as we move later into the century, so things get a whole lot warmer, many degrees warmer. We're already at Witwatersrand sitting at just under 2 degrees warmer, and significantly drier as well. We're currently sitting at about 10% drier than the climate of a century ago. And this plays through in important ways, for instance, in the river system. So now Witwatersrand is located where the Vaal River rises, the Tugela River rises, and the Pongola River rises. They all arrive, at the sort of area of Witwatersrand. And so the trends in river runoff in that area are really very indicative of what kind of the future holds for South Africa. And what we find, much to our shock and horror, and we have a very good runoff record there. There's been a station operating on the Slung River, which drains that system since 1947. What we find is a 60% reduction over that 70-year record. And that's a shocker because the rainfall's only gone down by 10%, but the runoff has gone down by nearly 60%. And the reason for that is that the runoff, results as an interplay between rainfall and evaporation. And because of the rising temperature, the evaporation has gone up a whole lot at the same time as the rainfall has gone down. The second reason is that the hydrological system is an amplifier of the climate system. So typically, if your rainfall changes by, let's say, 10%, you would expect approximately threefold multiplier on that for changes in runoff, just due to the nonlinearity of the hydrological cycle. So the other issue which raises concern over South Africa is drought, and particularly multi-year drought. So anyone who's followed South African history and agriculture knows that this is an arid country, and we have had droughts going back as long as there have been records. That continues, but there's some new spins on this. The one is that the probability of multi-year droughts, in other words, droughts where this year is dry and next year is dry and maybe even the year after that is dry, increases as the global climate mode moves more strongly into El Nino type circumstances, which happens with warming. There's a slightly different phenomenon which is going on in Cape Town and contributed to the multi-year drought there, which led to the sort of day zero crisis a few years ago in Cape Town. And that is that as these Hadley cells strengthen, so the westerly waves, which are those kind of cold front systems which sweep across the Southern Ocean and bring rainfall to the Southern Cape, get forced further south by the very strong Hadley cells. And so instead of sort of sweeping over the Southern Cape coast, particularly in spring and autumn, they actually pass through in the ocean. And that phenomenon is demonstrably strengthening, okay, over time, and is projected to continue strengthening into the future. But you know, we also have the strong possibility of getting day zero events here in Gauteng, because our storage system, our water here really comes from the Lesotho highlands and the same sort of climatic system as I demonstrated to you at Witwatersrand. And the water storage capacity in that system is only enough for about 2.5 to 3 years. So if we get a multi-year drought, we also, kind of run out of allocated water. The other side of this is the strengthening of tropical severe storms. So they get their power from warm ocean currents, warm surface water. And the surface waters in the Indian Ocean have been demonstrably warming over the period of record, as they have in all the tropical oceans, so the Pacific and the Atlantic. But I'm going to talk here about the Indian Ocean because that's the source of our tropical cyclones. Now, Southern Africa has been very fortunate up until now in that it has Madagascar acting as a kind of a defender for us. So when those rotating macro storms called tropical cyclones, they ramp themselves up over the warm ocean waters. When they go over land, they lose their oomph. The water is still there, but they stop rotating, and the high winds can tend to die out. When they go over land, they become what we call a cut-off low, and they just dump large amounts of rainfall on it. So around the world, we've seen an increase, not so much in the numbers of tropical severe storms, as in the intensity. The amount of energy contained in that whole system has been creeping upwards. And there's also a suggestion that they are moving polewards. And if you look at the sort of location of Madagascar and South Africa, if those storms, which always track from the east to the west, no longer first pass over Madagascar and kind of lose their power there, they pass south of Madagascar, then they hit the South African coast, somewhere between sort of Maputo and Durban. And so that's a potential concern for us. Let's talk a little bit about agriculture. It's true that a little bit of warming in certain parts of the world actually improves agriculture. If, for instance, you're growing wheat in Saskatchewan and you warm up by 2 degrees, it's not such a bad thing. You can get a higher yield out. And that's because a lot of those areas are on the left-hand side of that sort of generalized response curve I drew there, which is true for all crops. It can shift a little bit to the left and a little bit to the right, but all crops and livestock show a curve like that. And if you're below the optimum, and that optimum for crops sits somewhere around about 30 degrees daytime, summertime temperature, then a bit of warming actually accelerates grain production and filling, etc., provided you've got water supported. But if you're on the right-hand side of that curve, warming actually decreases your yield. And that's already the case in South Africa. If we take the yields of our different crop growing areas and plot them against the mean temperature in that area, we see, in fact, a negative curve, not a positive curve. In other words, further warming leads us to loss of production, not increase. There's a very similar relationship which applies to warm-bodied animals. That includes us, of course, but it also includes cows and sheep and all those livestock. They have an absolutely fixed body temperature. And as the atmospheric temperature rises towards that body temperature, so the ability of those animals to do, to be productive, to be reproductive, and to put on mass declines precipitously and eventually they die. And so, those vast areas of the interior of South Africa, which are not suitable already for growing crops, but we do use for animal production, rapidly become unusable for those purposes. And very similar things apply to human health. Yes, there are impacts on things like human, vector-borne diseases, things like malaria, etc. But the big impact is actually through high temperatures. As South Africans, we like to think that we're tough. We can do hot temperatures. I've got bad news for you. We're just warm-blooded animals. Our body temperature is also, 36.7, as we are repeatedly told these days. And as it gets hot, for every 2-degree warming, we can only do about a half as much work, physical work. So, if we're looking at a 4-degree warming over South Africa, that's a 4-fold decrease in the amount of physical outdoor labor that can be done before you get heat stress. There are some other issues associated with higher temperatures, particularly around water quality. My hydrologist friends always point out to me that you don't actually ever run out of water. What you do is you run out of drinkable water. The oceans are full of water, you just can't drink it. And the problem with inland water is as the temperature goes up, so its quality declines. And so it becomes much more difficult to bring it to a usable state. South Africa, prides itself on its, mineral resources, but it also has a remarkable endowment of biological resources. We are one of the 10 most biodiverse countries in the world, and increasingly our economy is built on the so-called bioeconomy, on living things. That includes agriculture, but it also includes, ecotourism and, things made out of natural products, etc. And that part of the economy has been the part that has been growing most strongly at a time when manufacture and primary minerals have been declining. But, climate change makes all of that a little bit dodgy. And particularly in the second half of the century, climate change becomes the major threat to biodiversity. Right now, the major threats are land use change, overharvesting, invasion by alien species, etc. But as we move forward into the century, so almost everything is outside of its climatic envelope. And in the distant past, things could move if they had enough time to find new niches. But we've so fragmented the landscape that that's really not possible anymore. And so we face all kinds of issues of, well, what do we do with all this biodiversity? If it's stuck on a mountaintop somewhere, do we just let it go extinct, or do we move it, by hand to some other mountaintop? How do we reassemble the ecosystems and all those kind of challenges? What grabs the headlines is the climate-related disasters. I've talked about Cyclone Idai, which is the second most mortality-inducing severe storm in the Southern Hemisphere on record. We've seen things like landslides in South Africa brought on by severe rainstorms. We've seen the massive increase in large-scale fires in the Southern Cape and various other parts of the country. And, all of these things are relatively rare events. So you've got to look at sort of what are the probabilities of rare events. Those are always very tricky to do, but there are unmistakable increases in the occurrence of severe storms, including cyclones, but also giant thunderstorms, which we call supercells, the resultant flooding and fire incidents in South Africa. There are also some local impacts of global climate change, which work not through necessarily the climate system, but through human systems. For instance, the South African economy is heavily built on coal and coal-produced energy. And as the world moves away from that, particularly by denying finance to coal mining and coal-fired power stations, so that leaves us kind of high and dry. There's also other things such as the northern developed countries would far prefer not to spend a lot of money fixing their carbon emissions, but for instance, let's plant trees instead. Oh, we don't have space to plant trees. Let's go and plant them in Africa. and there are schemes to plant 1,000,000 square kilometers in Africa in places which actually wouldn't support trees and where trees don't belong. That includes the Sahel. It also includes on their maps large parts of the northern provinces, northern interior of South Africa, which we all know are not tree-growing places. There's also obscure things like there's a big push internationally to eliminate meat from diets, which broadly speaking actually is a good thing from a climate perspective and a biodiversity perspective. But if you continue it to ridiculous lengths, what it means is that livelihoods in Africa, which are based on livestocking, then become even less able to provide a living. Sea level rise, you would think, is something that occurs equally around the world. Interestingly, it doesn't. Although the mean sea level rise goes up by a certain amount, what actually transpires in particular places depends on how steep the slope is, both out in the ocean, the bathymetry, and on land, but also all kinds of interesting circulation issues in the oceans. So South Africa, by and large, the country of South Africa, is relatively well protected from sea level rise of the amount that we're talking about. But some of our neighboring countries really aren't. So for instance, Mozambique is hugely exposed, as in Nigeria. Any place where the cities are built on deltas, for the amount of sea level rise, which is fairly inevitable over the next century, will actually suffer some serious problems. And then there's an interaction between climate change and just general food production problems. We have to double global food production over the next 50 years, not because the population is doubling, it's only going up by about 20%, but because of dietary change, and particularly dietary change in China and India, consuming animal-based proteins, which means that larger and larger areas have to be planted to maize and soybean to supply that. And you can say, well, South Africa doesn't have to grow its own food. We're a dry country. Why don't we just do something we're good at, like mining gold or something like that, and then we'll buy in our food. The problem with the food system is that nobody trades it when you come to crunch time. And we've seen that repeatedly with food shortages in the past. When there was a crisis in rice production a few years ago, you couldn't buy rice, on the international market because countries satisfy their domestic markets before they export it. And then finally, you can say, well, we'll just let the rest of the world go their own way. We'll just run our own little economy here. But for an export-linked economy like South Africa, that's really problematic, because if you're producing your goods under a lax climate change mitigation regime, countries where you're exporting to simply impose a border tax adjustment on you. Say, well, look, we're telling our companies they have to pay carbon taxes. You aren't paying the carbon taxes, therefore we slap them on at the border, and then they benefit, also from the fiscal income from that. Can we do anything about this? Technically speaking, we could still keep the world from rising more than 1.5 degrees above the pre-modern mean temperature. I think that is politically and economically at this stage a pipe dream. I think that we're most likely to, in fact, overshoot that and hopefully come down again. There's nothing magic about the 2 degrees Celsius limit that was established in Paris. We already see serious impacts of climate change, and they get much steeper between the target which the developing countries wanted, which was 1.5, and the target which was eventually agreed at, which is 2 degrees. So there's an increasing amount of impact as we get warmer and warmer, and it just goes steeper and steeper. And so the 2 degree was just a kind of a negotiated compromise. I think we will probably overshoot that as well. And coming down, to a stable climate requires not that we reduce our emissions by a few percent, but by, in fact, reducing them to essentially nothing. And in fact, if we're in that overshoot state, we actually have to have these things called net zero emissions. And we don't really have the technology to do that yet. We can think of some theoretical ways of doing that, but at scale, that there's nothing really on the horizon. And so that's why, I suspect that we are going to overshoot those targets currently on the basis of present commitments, we're actually looking at close to 4 degrees targets globally. And of course, in South Africa, that means twice that. In other words, hitting those 8-degree warmings in South Africa. But you can draw all kinds of graphs like that with squiggly lines and different pathways and scenarios. I really like this approach because it greatly simplifies things. If you just take the cumulative emission of greenhouse gases expressed in CO2 equivalents and plot them against the cumulative warming, which comes out from both the observed record and hundreds of model runs, it forms an absolutely straight line. Okay, it's very simple. The more carbon dioxide and greenhouse gases you put into the atmosphere, the more warming you get. And so you can choose any limit that you like. We can fight about whether it's 1.5 or 2 degrees or 2.5 degrees, whatever line you choose, on the horizontal line there, you will get a band of total cumulative emissions, which is permissible and is consistent with that temperature future. And the rub is this, is that we've already emitted, say if we read that on the CO2 emissions axis, around about 3,000 billion tons of carbon dioxide. And running out of fossil fuels is not going to solve the problem, because there's about 4 to 6 times more known reserves of fossil fuels than that limit that we have to get to. So we're not going to run out of those things. In order to stay within that bound at the 1,000 gigatons carbon or 3,800 gigatons CO2, there's just that tiny amount left. And that's the budget. That's the global budget for now, for the next several centuries of what we can emit. And the big fun fight is of who gets to emit that. Do we grandfather in, the big emissions in the past, which by the way includes South Africa, or do we say, no, the developing countries have to have a bigger slice of that to allow them, to raise to the level that they want? And that's why this is such a difficult discussion and such an inescapable conclusion. Because the other thing which becomes abundantly clear from this graphic is that 3/4 of the known reserves of fossil fuels, coal, oil, gas, have to stay in the ground. They can't come out. If we want to have a livable future, they have to stay underground. And that, of course, is shocking if your, for instance, your share price is built on the fossil fuel reserves that you have. Suddenly, 3/4 of your, underpinning wealth disappears. So that kind of brings us to the nub of the point, which is that climate change fundamentally actually isn't a technical problem or a biophysical problem. We understand that stuff. That stuff's pretty sorted. There's obviously still a lot of things with an error bar and uncertainty there, but the fundamentals are extremely well established. But what this is basically is a relationship problem. And as a result, it has these deep value-based and ethical implications. It's about how we relate to ourselves, our consumption patterns, our expectations, etc. How we relate to others. There's deep inequities in climate change, in who benefits and who pays. As usual, it's usually the marginalized and poor people who live in the hot, dry parts of the world that suffer the most. Relationship to nature, we share this planet with something in the region of 5 million other species, okay, many of which are deeply endangered by the climate changes which are coming on, and especially to our relationships to the future, because the kind of benefits of our lifestyles and our energy systems are reaped in the here and now, but the bill, comes to be paid in future generations. And how do you do that in an equitable way, given that future generations aren't here to sort of debate the odds with us? So that's the presentation. I'm very happy to accept questions. I believe they're first coming in on chat, and they'll be related to me by Hugo. And then if there's any time over, we will take verbal questions as well.
Okay, thank you, Prof. That's very interesting. Andrew, I know you've got questions, but I'm going to give you final questions because I know you're going to be the contrarian. So I first want to clarify things. I have actually quite a few questions with you, and many of them is actually just for clarification. you made the point that climate is measured by mean temperatures. It is not, the maximum minimum tomorrow today, and that mean temperatures are actually quite predictable over time. So is there a difference between average surface temperature and mean temperatures, or is it the same thing? It's just the first point of clarification.
So the sort of reference number that everyone uses is something called GMT, which doesn't stand for Greenwich Mean Time. It stands for Global Mean Temperature. And that is actually the temperature just above the surface. It's what you would measure in a weather station, where the thermometer sits at actually 1.5 meters above the surface in that little shielded box. And there's an equivalent in the oceans. And so the trick here is that, we have weather stations distributed all over the land parts, not evenly. We have more in denser parts of the world and fewer in sparser parts of the world. And, there's more in developed countries than in developing countries. But then also, what do you do in the ocean? We only have ships, passing over there, taking these temperatures. So now you've got to pull these all together and work out a global mean. You don't just take the whole list of them and add them up and divide by n. You actually have to weight them by the area that they're representing and also correct them for known biases, such as changes in instrumentation or the fact that weather stations which are in urbanized areas get warmer because of the urban heat island effect. So you take away all those things and then you put them together, and that gives you the global mean temperature, which is the same thing as talking about air temperatures. The air temperature in the kind of space where we live, not the air temperature,
No.
thousands of meters up in the air, or at the.
So my view with measurement theory is anyways been it doesn't matter what you measure as long as you measure it consistently, you can pick up trends. And I think that's just the point to make. It was,
So that is incredibly important. That whatever indicator you choose, that you do your analysis in a consistent and unbiased way. Okay. If we were to have our preference, the best thing for us to measure would in fact be the integrated temperature of the deep oceans, because that is where all the energy is going. Okay, the atmosphere fluctuates. Think about it. It was cool this morning, it's hot now, it'll be cool again tonight, it's cool in the winter, it's warm in the summer. It fluctuates all over the show. But the integrated temperature of the oceans actually pulls together all these climate signals and is growing up, kind of smoothly and continuously. But that, is something that we've only been able to measure accurately, in the last few decades.
Okay, just remind everyone, please type your questions first and then I'll call them out and then I'll give it for raising hands. Okay, I've got another question here, which I wrote down. It's again a point of clarity. You talked about water storage. Now, I spoke to Professor Andrew Turton last Friday, and water in South Africa is just mismanagement. Now, I understand that climate plays a role, but I think we should not, give the government or people in that who are responsible for managing the water any leeway by saying it's just a climate. He made the important point that water should not be treated as a stock, but a flux. So we should not see that we're running out of water. We need to recycle the water, essentially.
No, I agree with both of those points. Okay. For instance, even the Cape Town crisis had a huge component of misallocation of the water. In South Africa, as in most places, somewhere between 2/3 and 3/4 of the water is used in agriculture. And there's much more efficient ways to use it in agriculture, and also ways that you can use it in the economy, which generated much more value add than spraying it on crops. And so, the issue is not only the fact that our water supplies are declining and becoming more polluted, but also how we divvy them up among particular uses, and that's a management issue.
Okay, then I've got a question here for you regarding agriculture. Okay. Yeah. What is your view on regenerative agriculture, first of all? And I think as I said, this is a point of disagreement. I don't think we're going to run out of food. I think it's a very Malthusian argument. Farmers are very innovative and we find new ways to do so. It's just the point of disagreement. And then just a point, can't we sequester just the carbon in the soil?
So sequestration of carbon in soil is one of the more promising ways of getting carbon out of the atmosphere. And regenerative agriculture, which I'm just going to explain for a second, for the broad leadership here, is ways of doing agriculture which help to rebuild soil carbon stocks. And in South Africa, we've seen a massive switch across to that, not for climate change reasons, but for essentially drought avoidance reasons and sort of farming economic reasons. So we're seeing a huge switch into what's called no-till agriculture, which is one form of regenerative agriculture. So it does build up soil carbon stocks. There's no question about that. We can have a debate about, what the upper limit of that is, because there is an upper limit. The soil gets saturated with carbon at some point, and what the sort of, side consequences are of now treating, the crops with herbicides in large volumes versus plowing, but that's not the question. The question really is, does this have an impact on the climate? Yes, it does. Small, but real. And overall, my opinion on regenerative agriculture is on the positive side. Rather, I see the arguments for and against, but broadly speaking, I think that the arguments for are carry the day.
Yeah, and just to extend on that, it's almost an agreement among denialists and everyone. Okay, so I'm not going to go through all my questions because there's too many of them. I've just got another question for you. Okay, this is a question relating to models and to probabilistic models. So first of all, while it might be true that the storms are getting more severe, it is true also that fewer people are dying from natural disasters, and that's because we have building safer cities and we can design for it. So, I mean, is it really that cause of concern? I understand the storms are getting worse, and yes, there's been a more severe storm, but the amount of people dying historically from natural disasters is undoubtedly going down. So, this is the
well, I would be less confident in that statement. The likelihood of dying, in other words, the proportion of people dying from natural disasters could well be going down. But the absolute numbers, I'm not completely convinced by that. And when you sort of go forward, and it's not necessarily a question of dying of these things, if your sea level rise, goes up by a meter, which is sort of the bottom end of projections for this century, then about 1 billion people around the world have to move. So they haven't died, okay, but they have to go and settle somewhere, and that's a fairly major consequence. And so
but it is manageable in my view. I mean, you can build like the Dutch.
It may well be manageable, and the Dutch, are planning some enormous seawalls. That's not that easy if you're a Bangladesh or a Mozambique, and if you do the sums, the cost of doing nothing versus the cost of addressing and mitigating climate change, already the numbers of the cost of inaction are several times higher than the cost of action. So it just doesn't make economic sense. Even though there might be a technical solution, there's also a technical solution which says we don't have to do that. Okay, let's rather invest it in a decarbonized energy economy, and then you wouldn't have to spend that. And by the way, it's 3 times cheaper.
So, okay, those are again, let me tell you my biggest criticism against, I'll say your speech, but against predicting the future. We've seen with this pandemic how projected models have gone completely wrong, from the beginning. The Imperial College model, for example, we've seen time and time again how population models get it wrong. The world is not overpopulated. If anything, it's underpopulated. The world is getting better economically on almost any measurable index, for example. No, I understand the carbon dioxide has gone up, but it's only going up in developing countries. It is going up in China and India, and it is actually
emissions, presumably, rather than concentrations.
Yes,
concentrations go up everywhere in the world.
Yes, emissions have peaked in France, for example, in the 90s. And the point is just, here's the big elephant in the room. Okay, but according to UN projections, 1/3 of the world's population by the end of the century, when your models predict sea level rises, etc., 1/3 of the world's population will be Africans, people from Africa. I'm sure you're aware of that. And Africa wants to develop. These guys want to live the same lifestyle we live in Europe. They want to live the same lifestyle that white South Africans live, etc. And to do that, you need energy. Now, I am not convinced, and I work in the energy sector, that renewable energies are worth it, to be frank with you. I think it's a scam. I think it's much sensible to invest in nuclear energy, for example. So I just want to, you need energy dense energies to power a modern civilization. And how are we going to solve that problem? And my suggestion is, what do you think of nuclear?
There's two embedded questions in there. The one is the relationship between development and energy. And, we know that there's a strong relationship there. But there's 2 points about that relationship. So if you plot it either at the national level or at the individual level, what you see is that there's a positive relationship, but there's an enormous scatter around that points around that graph, and that graph actually saturates above a certain level. In other words, you need to get to a certain level of energy sufficiency, and then you get human well-being increases. Beyond that, you don't get further human well-being increases. And secondly, at any given level of energy supply, you can have the same human well-being for vastly different amounts of energy. And so the argument there is that we should be aiming, as particularly for those people who below that saturation point of the well-being increase with energy, to make sure that they're on the lower emissions path and not on the higher emissions path. And that really is the way forward that I see for Africa. I don't see any necessity why Africa has to follow the same tired old path that the rest of the world has followed. You start with agriculture, then you move into dirty industry, then you move into advanced manufacturing, and then you move into the knowledge economy.
They can leapfrog.
That's kind of given, that's development theory, 101. But there's nothing essential about that. And many of the reasons why the developed world has been able to take that pathway is they've been able to push their dirty stuff, into the developing world. So China is going to, have zero emissions by 2050, they claim. They're doing that by developing coal resources and dirty industries in Africa. And why would you be the willing recipient for that? Why don't you, in fact, actually just short circuit that developmental sequence and go, for instance, directly to high knowledge input economies? Whether you're in agriculture or in mining or in manufacture, you don't have to follow the same route. You can, in fact, for instance, go to an agriculture which has much greater nutritional outputs for a much lower climate and other environmental impacts. We know how to do this. For instance,
that has happened to an extent. The Chinese did not start with the Industrial Revolution the same way the UK started, for example. Okay, so it is happening.
We've seen that in certain aspects in Africa as well. The most famous example is going straight to cell phones instead of going via fixed wire technology. So it is possible to do the so-called leapfrog.
Okay, but I just want to have a final point that should not be missed here, and that is renewable energies. The Germans had the Energiewende, and they actually increased their carbon emissions because they got rid of nuclear energy. California is doing it, and they increased energy poverty. You see homelessness in California. People are leaving California at the moment, and I am just worried that I would agree with you. If what you say is true, etc., that we need to be smart about it, but we should also not be stupid about it. And my view is just the word renewable energies, the solar and the wind, is so intermittent and it's actually destructive. And the answer to that is nuclear energy. And nobody that's green wants to hear this. Green is the most green energy. It's a less carbon. It's most energy dense. It works. It's safe. I designed the reactors. Maybe I vested interest in it. I don't know. But the fact is that I would like for the pro climate change crowd to become honest about nuclear energy, because it's the same people that is against nuclear energy that says the climate is dying.
So I actually personally don't have a insuperable problem with nuclear energy. But I have had some experience with the nuclear industry as a whole. My very first tasks as a young graduate student 40 years ago were, looking at revegetation on post, nuclear disposal sites. And I learned something about the nuclear energy industry, and that is it never tells you the truth. Okay, it has a built-in, kind of tendency to obfuscate. And one of the key issues in South Africa against nuclear is not the environmental impact, but the economic impact. And when you try to get numbers out about what will this cost per kilowatt hour, the numbers, even those that you extract internationally, are just so much higher than the alternatives.
But
much higher than
you know why that is. I can give you 2 reasons why that is. Okay.
Yeah, I have no idea why that is, but it happens all the time, and they never actually are upfront about, kind of where are those numbers coming from.
So there's 2 reasons why that is, then why the Chinese can get away not doing it. The first one is that nuclear industry, in my view, is over-regulated. It's completely absurd how they manage it. They can manage it like they used to do in the 1950s, and the prices will come down. The second reason is the Western world defines decommissioning in an utterly absurd manner. The Chinese look at decommissioning this way. They say any material that's radioactive from a nuclear plant is considered to be radioactive. That's logical. The Western world says everything from a nuclear plant is radioactive, and that increases the cost of decommissioning. And then the greenies tell us you cannot afford the decommissioning of the cost. Now you're decommissioning a plant, you take a diamond blade and you cut it up. It's not complicated. Anyways, that was my final comment. Andrew, you're going to be next speaker, and I'm just saying, preparing you a bit for a chop.
So I actually, don't particularly want to get into a discussion about nuclear energy, because I have no, particular skills in nuclear energy. If you want to have a discussion about climate change, I'm perfectly capable of.
Right. No, fair enough. Fair enough.
My expert inputs on nuclear engineering, I don't pretend to be a nuclear engineer.
Okay, I'm not holding it against you. Thank you again for the discussion. Okay, I'm going to leave it over to Andrew, and Andrew, keep it civil, please.
Of course, yes. No, I'm terribly polite. I'll be polite now. So thank you very much, Professor. Enjoyed the talk. I was most interested in your observations about the local changes. That's most interesting to me. By the way, the Libertarians were once in Wackerstroom, and I thought it was a wonderful place. And I'd love to go back there again. I thought the bird life was marvelous, even though I don't know much about it. On your talk, you didn't deal very much with the main themes of global warming. You dealt more with local effects, which I find very interesting. Okay, here's the thing. There is no doubt whatsoever that the world's temperatures have increased from 1850, mentioned those 2 days, to now. No doubt about it whatsoever. It's increased by about just under 1 degree centigrade. Also, no doubt whatsoever that carbon dioxide has risen, and we've increased it. Not volcanoes, mankind's increased it. And we should congratulate ourselves. It's the best thing we've ever done. Carbon dioxide levels are much too low in the past, catastrophically low in the ice ages, and we've increased it. A jolly good thing. The world is greening because of it. What caused the slight warming since 1750? Well, the one thing we can rule out completely is carbon dioxide, is rising carbon dioxide. Why? Because I showed a graph of 550 million years going into the past, carbon dioxide versus global temperatures, and there is no correlation between the two. Carbon dioxide is a greenhouse gas. It's a weak greenhouse gas. It's only got one relevant absorption band at 15 micron, which is already saturated to the peak. So adding more, in theory, adding more should have a slight effect. In practice, it doesn't seem to have any effect at all. And this is because of overlap with the absorption bands of water and because of negative feedback, which makes our world stable. You mentioned solar, and so you ruled out solar because variations in total energy and the 11-year sunspot cycle. Well, neither of those is the important thing. The important thing in the variations of the sun is not variations in TSI, in total energy. That's a minor thing recently. The 11-year cycle of sunspots is also noted, but what's very important is the long-term cycles in the amounts of charged particles and the strength of the sun's magnetic field. That is all important. And that's the one that has driven temperatures for at least 10,000 years. So for example, from 900 to 1200 AD, in the medieval warm period, all over the world on all 5 continents, backed up by over 1,000 scientific studies, massive amounts of historical record, temperatures are rather higher than now, while carbon dioxide was 280 parts per million, much lower than now. Before that, the Roman period, When Julius Caesar was born, temperatures were about 2 degrees higher than now. Carbon dioxide was 280. In the Mann before that, it was even hotter. Carbon dioxide was lower than now. Never have we seen carbon dioxide to drive global temperatures. The couple of things.
Edward, can you first respond to that before you get into the other question? Is that fine? Thank you.
So the normal statement, about rising CO2 being a wonderful thing because, it fertilizes plants and it's the feedstuff of production. There is an element of truth in that, and that gets built into, for instance, all our agricultural production models. We get an increase as a result of the rising CO2, but it saturates. And it saturates in natural ecosystems actually very low, at almost the level that we're at now. And the reason for that is those crops aren't carbon dioxide limited. That's not the issue. They're water limited or they're nutrient limited. And so having abundantly pouring carbon dioxide on them doesn't really help at all. In terms of the statement, well, this brought us out of the ice age. We were out of the ice age already in 1750. We had been for about 10,000 years, and there isn't another one due for another many thousand years. It is true that it's unlikely that we will actually, in the foreseeable future, and by that I mean millennia and that sort of time scale, go back into an ice age, because we've pushed the global carbon cycle into a mode which we haven't been into for an awful long time. So it was in this fluctuating glacial interglacial thing where it bounced between 280 and 180 degrees Celsius, and that was only possible with a certain amount of carbon in the system. We're now way beyond that point, and so we're very unlikely to ever go back into an ice age. So you can tick that one off the worry list. The assertions that there is no relationship between carbon dioxide and temperature into the past are absolutely baseless and not founded in science. You can look into the basic physics of this, very well known. You can look into the data on this. You can look into all the experimentation on this. You can look into the records. Going back 550 million years is complete nonsense. We have no good carbon dioxide proxies further back than about 600,000 years. So that is, just completely insupportable scientifically. And I know you're going to dispute that. That's fine. I'm a carbon scientist. Okay, I work on carbon dioxide. You can either accept my statements or you can accept Mr. Kenny's statement.
Can I reply? Okay. I've never said that rising carbon dioxide got us out of the ice age. That was, we don't know why, but something to do with eccentricities in Earth's orbit. We don't understand why, but that seems to be the only likely explanation. I never said that. All I said was when we got out of the ice ages, temperatures then rose, thank goodness. That released carbon dioxide, and carbon dioxide increased from about 180 to 280. Out of the danger zone, but still much too low. Mankind has now increased it more. But how on earth can you deny the science that shows you? But there's all sorts of ways that you could measure carbon dioxide in the past, not terribly with huge errors of margin of inaccuracy, that's for true. Great science, I can show you study after study after study where they've looked at carbon dioxide since the beginning of the Cambrian and shown these studies. So in the Cambrian period itself, carbon dioxide at times was over 6,000 ppm. This is at the time of the most productive ever, the Cambrian explosion of life forms, where the best scientists in the world have shown carbon dioxide was higher than now. How can you deny this? It seems to me that you are the denialist. You are denying this.
I'm denying the statement you state that there's no association between the two. At that time, the world was much warmer. But the critical issue is we weren't here. This is an irrelevant discussion. Anything more than a discussion at the decadal to century time scale is completely irrelevant to this discussion.
Absolute nonsense. Of course, what happened in the past is vital for understanding our planet. Are you going to say that the extensions of the past, we don't have to bother about them? We weren't there at the time when the dinosaurs were wiped out. What an absurd thing to say. Of course, we must understand the past. I wasn't there at the time of the American Civil War. Doesn't mean to say it wasn't important. just to say, as far as food crops are concerned and carbon dioxide, horticulturists put a lot of carbon dioxide into their greenhouses to improve the production of plants there. In the past, carbon dioxide has averaged about 2,000 parts per million. That's what plants are used to. Optimal level, I don't know. It seems to be between 1,500 and 2,000 parts per million. That's what happened for most of plant life on Earth. Can I just go into some of the other points now?
I am, in fact, an ecologist who works on carbon metabolism of plants, and you're speaking complete rubbish.
No, you're speaking rubbish. And by the way, there's two types of
okay, let's just move on from the carbon one. Okay,
right,
you're in the disagreement that's not going
okay.
to is not going to budge anyone. You know, let the audience decide for themselves.
Yeah. Okay. Sorry. So excuse me. Okay. As for I disagree with you, Mr. Chairman. You say storms are getting worse. They're not getting worse. If you look at every single measurement of extreme weather, hurricanes, which are a type of cyclone, droughts, wildfires, which are one of the factors that leads to them is the weather. None of them are increasing. None of them are increasing over the last 100 years. In fact, but if you look at the past, if you look at the cold ages of the past, I don't know if you can see this. This is a book written about the 17th century. Then climate extremes are much worse than now. Storms were worse than now. Floods, droughts were worse than now.
Just a question, storms, what's your measurement for that? Because are you talking about the severity and the intensity of the storm, or the number of people dying? Because those are two fundamental things.
Number of people dying is not a very good measure. Because, you know, if you have an earthquake in
I was referring to number of people dying.
No, that's not a good measure. So with hurricanes, for example, the three measures are the pressure in the middle of the eye, the maximum wind velocities, those are the two ones. And if you look at those, they are not increasing. And then, over the last 100 years.
So that's simply not true. You know, the only way that we can get reliable data on hurricanes is in the post-satellite period, because, for instance, the wind speed, you know, the anemometers that they had even 50 years ago simply blew off their axles at those temperatures. We have almost no records.
You have satellite imagery. You have temperatures in the eye of the lower the pressure. The lower the pressure, the more extreme the hurricane. And we've got
not absolutely. No, that's not.
Well, that of course it is. In general, the lower the pressure in the eye of the hurricane.
Okay. The way we work out the intensity of the storm is the integration over the storm of the energy involved in it. In other words, we get the wind velocities, we integrate them over the volume of the storm. And that's only been possible since the satellite era. And there has been an increase in storm intensity measured around the whole world over that period.
Okay, Andrew, I'm going to unmute you again to respond to that, but I don't want people to yell over each other. It doesn't make any sense. Okay, I guess I get that you two are on the opposite side of this, but you were here on Monday and you gave your interview, and you know my views on yours as well. So it's not that I am taking sides. I have to be fair to the speaker. Okay, I'm going to unmute you and then you can respond. But I think, okay, storms, you disagree. You disagree on carbon dioxide, you disagree on storms. I don't see any benefit in continuing, you know, we can look at the data. And I guess that the contention I'm seeing here, okay, between the two sides is Andrew is looking at a long period of history and he's comparing that data, and Prof is saying, well, we actually have good measurement from the 60s or 50s onwards, and we're working with that period. And I think both of you actually agree the climate is getting warmer. It is just one is a longer, one is a shorter period. Okay, Andrew, I'll unmute you, and I think just ask your next question. Thank you. You can unmute yourself, I think. Sorry, Andrew.
Sorry, I don't know what Professor Cole's qualifications are, but mine are just in physics. I know nothing about botany or that sort of thing. But just looking from the point of view of physics, I'll make a prediction now. I'll predict that if the sun was very active in the 20th century, and that's why we had that global warming. It's because of the sun. It's not because of carbon dioxide. The sun has recently become very, very quiet. But of course, there's other cycles on Earth, the PDO and so forth. Here are my predictions. If the sun remains quiet, and I've got no idea whether it will or not, I predict that 2100 will be a little bit cooler than now. No ice age, that's a different thing. A bit cooler than now. If the sun becomes active again, as it was, say, 30 years ago, the increase in temperature will be less than 1 degree from now. In other words, it'll still be cooler than it was when Julius Caesar was born. By the way, this thing about we must decrease temperatures below 1.5 above pre-industrial time. What does pre-industrial mean? Does it mean in the middle of the Little Ice Age in 1750, or does it mean when Julius Caesar was born in in BC and 100 BC? It was warmer when he was born than it is now. Are you going to blame chariot racing for that? Those are my predictions. The idea that it's going to increase by 2 degrees or 4 degrees is absolute nonsense with no basis in physical science at all.
Am I unmuted?
Yes,
so,
you're muted.
You know, tens of thousands of physicists, mathematicians, climatologists, and weather stations disagree with you. I would be very happy to take you up on your bet, but I'm not going to be here to collect on it, so that's a bit silly. You know, which reference level we choose. We choose pre-industrial, you know, because it's intuitive to people. You could equally choose, and people very frequently do, the so-called climate normal period, which is the period 1960 to 1990. It's just a reference period, you know, and the targets change depending on what baseline reference you choose. If you choose the 1960 to 1990, then that agreed target is 1.6 degrees Celsius, not 2 degrees, because there was 0.4 between the start of the Industrial Revolution and then. It's irrelevant to this discussion. We actually have no idea what the temperatures were in Rome 2,000 years ago. We have proxy measurements. No, we've got proxy measurements, but the error bars on the proxy measurements are extremely broad.
So
there were no thermometers.
Can I just have a clarity point here? What you're saying is, because my understanding from the previous temperatures is they got it from the bubbles in the ice cubes, and then they try and correlate from that. Okay, and I think you're in agreement with that. And what you're now saying is that in this, call it modern era, since the 50s or 60s, whenever measurement started, we have more precise measurements, and you cannot compare the apples to the oranges. So
we have fairly precise measurements of climate since about 1850 with the invention of, you know, modern day thermometers. Right. We've changed technology several times since then, but the precision has increased, and that's, you know, perfectly adequate. Measurements of carbon dioxide and other gases in the atmosphere, direct measurements started in the late 1950s with the development of infrared gas analyzers, etc. We are able to push that back. So we push it back in the time period up to about 600,000 years ago with the ice bubbles in the ice cores. But that doesn't have an annual time resolution. You know, that ice core is very long, it's about 2 kilometers, but to get a sufficient volume of ice out, you have to take, you know, a certain amount of it and bubble it out, and that doesn't give you, you know, kind of annual variation. To give, in the last about 2000 or 3000 period, we actually use something called firn, which isn't ice bubbles in blue ice. It's semi-compacted snow. It's kind of the top layer of snow. Right. And again, there's a limited resolution. These are all proxy measures. We have other proxy measures, tree growth rings, stalactite growth rings. We use all these things, and that's how we can reconstruct the fact that the global climate has actually been remarkably flat since about 10,000 years ago, the so-called Holocene, which is what corresponds with our, you know, rise of modern Neolithic civilization. You know, we put all of those proxies in, but still, if you look at the error bars on that, they're, you know, way larger than we could say, you know, it was this temperature. Because
that was my question on Monday to Andrew as well, is the further you go back, the higher your variance becomes. Okay, that makes anyone who has done any measurement theory would know that. So I just have a question on that then. So your point of reference is the 1850s, I guess, and you're saying since the industrial age, things have gotten worse. And I think, from my understanding, Andrew doesn't really disagree that temperatures have gotten high. He disagrees with a lot of conclusions, and he looks at the historical record and he takes that into account. And you're saying we need to really start at 1850. That's really the point of departure. Is that correct?
So in terms of understanding Earth system processes, we go back all kinds of distances. You know, you even go back millions and millions of years,
Right.
but you don't try to build a regression relationship between CO2 concentration in the atmosphere and atmospheric temperature using records which are, you know, tens or hundreds of millions old, because the uncertainty on each of those axes is just way too big, you know, to be able to build a defensible regression. So we typically, you know, depending on what purpose you're talking about, if you're talking about changes taking place at century sort of timescales, we typically use then those ice core type records because they have that kind of resolution. Okay, if you're talking about building model verifications, for instance, we actually use runs from the beginning of this century because that's where we have the most reliable records.
Fair enough. Okay, thanks for that. Andrew, I'll give you a question now. I just want another follow-up. There was the hockey stick curve by Michael Mann, I believe it was, and it's been highly disputed, right? It has been disputed by, I think it's McKintrey, and you just talked about the variation in the trees. I forgot the right name now, and that was apparently the criticism against him, and they were also saying that it is just an over-exaggeration. And unfortunately, that thing set the paradigm because that was an Al Gore's movie. It was everywhere. And first of all, do you disagree that it has been highly disputed? And then the second one is, because, you know, my problem with the climate debate has been, okay, I can accept your hypothesis, fine. But I do believe that there are people exploiting the situation to sell products and etc. And they are making exaggerated claims as opposed to be accurate. And my intention is, as a scientist, you would know you need to be as accurate as possible. So I guess it's just a question on the Michael Mann hockey stick. What is your impression of that?
So firstly, it's deeply unfair to call it the Michael Mann hockey stick. You know, he just happened to be the executive officer of the group within the global research community called PAGES, which was responsible for assembling the data for that. And therefore, you know, the US political system went after him, tried to have him fired from his job, okay, for doing this. And it is contested. How you measure highly contested, I'm not sure. If you looked at the number of people who are in support of a non-linear increase in temperatures over the past 200 years, I can phrase it that way, versus those who think that that is spurious, I would say the odds are probably 100 to 1. But there are still, you know, a number of people who have disputed it. Now, as it happens, this particular thing has gone to intensive examination, not once, but 3 times. Firstly, triggered by the US Congress and the whole thing, you know, that all got raked over. Secondly, a similar thing happened in the US, in the UK, and they called in the Royal Society. And then thirdly, you know, there was a whole discussion amongst competing biostatisticians who were arguing not so much about how you take the measurements, but how do you process them so that you can put together proxy records with different attributes from different sources, different places, et cetera, et cetera. And there were a bunch of disputes about that. Now, here's the thing that people, you know, forget to mention. It has been disputed, as I said, in very formal senses, at least 3 times. It's survived all 3. The conclusions of all of those, sometimes very hostile panels, was that there was a non-linear increase in temperature since the beginning of the industrial period. And we can debate about how big it was, your exaggeration point, or whether it was bigger or smaller, but we're talking about actually small differences here. We're not talking about the fundamentals. There was such an uptick.
Thank you for the clarity.
Unprecedented uptick.
Thank you for that. That's just the clarity. Okay, Andrew, I'm going to unmute you again, but please, guys, keep the temperatures low. Just unmute yourself.
Can you hear me now?
Yes.
Yeah, okay. It's just the hockey stick was completely fraudulent. It was a piece of fraud, and in my talk I explained in detail why it was. I don't want to go over it again. The establishment, a complete cover-up. So if you have a scandal that's bad enough, the cover-up is even worse. So Nixon made himself worse by the cover-up. Michael Mann, people said it's a fraud, so they took him to court for defamation. And they said, right, show us your computer could show us how we can. And he refused point blank to show what his codes are. So from a set of very bad data using terrible statistical methods, he refuses to tell you how he gets this result, which came out of nowhere. So it is fraud. The professor says that temperatures have been fairly steady over the last 1,000 years. It's completely wrong. In the medieval warm periods, which was from about 900 to about 1200, more or less, temperatures were rather higher than now. And the proof is there in the historical record. You go to Greenland now, and you can see the remnants, the ruins of a Viking establishment there, where they were growing crops, European crops, that you can't grow them now because it's too cold now. The temperatures then dropped into the Little Ice Age, and the Vikings abandoned the settlement. It's there. You can see the bricks, you can see the structures that they abandoned. This isn't some airy-fairy proxy or something. There's real hard evidence there. And the same thing around the world. Wherever you look around the world, everywhere, you can see the remains, the record of this period where it was warmer than now, from about 900 to 1200, when carbon dioxide was lower than now. Then temperatures dropped into the Little Ice Age, and we had the terrible, terrible times in the Little Ice Age.
I just want to ask Andrew again. Sorry, I'm just rephrasing. The Prof is defending his hypothesis. I understand you are disputing the claims, but we've talked about the temperatures. He disagrees with you. Again, like they can look at your slide, they can come to the conclusions themselves. He's disagreed with this. Okay, I'm the chair, I have to calm the conversation. Do we have another question? So I've got a question here from Viv in the comments. Okay. And I'm just saying, she says, okay, I'm not sure if I properly understood, okay, because everyone here is not a scientist. Everyone haven't gone through the data, and they don't have a physical background. But she's asking, how worried do Prof think we should be about this? Because we also face other issues, right? We face poverty, we face energy, we face water scarcity, unemployment. All this stuff has to be solved in a big net or series or holistic framework, if you will. I don't know how to frame it. Like what weight should we do to it? Because we can't throw all the resources at climate change, right? And I'm sure you'll agree with that.
Yeah, it's a good question, and part of the problem at the moment is we're seeing a whole bunch of really serious issues happening simultaneously around the world, and it's not an accident that that's happening. It wasn't just bad luck; they all kind of just happened together. It's because we're actually stretching the limits of the biospheric capacity in many, many ways. So we're seeing a biodiversity crisis going on. We're seeing a land degradation crisis. We're seeing a poverty crisis. We're seeing a this and then the other. And in fact, if you try to construct them as completely separate things, let's do whack-a-mole. Let's get on top of the climate change. Oh hell, that really screwed up the biodiversity. Let's fix the biodiversity. Oops, they all got cooked by climate change. You just can't succeed. You actually have to see these as a systemic, connected set of issues. And that's kind of one of the problems with, the Sustainable Development Goals, which actually everyone kind of agrees with. It's really hard to disagree with.
They're very lovely. Yeah. They're very lovely.
They're all lovely, but how can you possibly tackle 17 things? And the only way you can do that is by understand their systemic connections and say, okay, these things go together. We have to tackle them in this way, and that has side benefits there. So I am indeed actually very concerned about climate change, particularly in South Africa. I'm not more concerned about climate change than I am about growing inequality. It's a false dichotomy. These things, if they're not already related, will be very related in the future. So you actually have to teach. There's no point in saying, well, I can only focus on one thing, so I'm just going to pick this one, because something else, is going to undo all of that. You actually have no choice but to deal with these things to the best possibility you can simultaneously. I also have, like you, in fact, a great faith in the inventive capability of humans, but they only really deploy that when imminent and clear danger, is staring them in the face. And the nature of climate change is that the serious impacts actually happen some decades after you've done the deed. Because of the kind of inherent inertia in the system. And that means that is the fundamental reason why I think that we will go into quite serious overshoot and things will in fact become very uncomfortable. I think we almost certain to do that already. We're already seeing in South Africa, some major climate related issues. The question is, can we stay within an adaptable envelope? We already have to adapt. We're committed to something around about a 2 degrees Celsius change. But can we keep that in a survivable envelope? I don't know what the upper limit of that envelope is, but I know that it gets steeper and steeper and trickier and more expensive the higher we get.
Fair enough, and that's a very interesting point. My response to that would be that I think we're looking at these things through different paradigms. You should not say that my view is development must happen, and of course, if this is the issue, you need to address it, development through it. It needs to be part of your outcomes, if you will, and it's essentially a holistic frame of mind. And I know it was Einstein who famously said to Jan Smuts that the science that what will distinguish the science of the last century from the 20th century would be between holism and reductionism. So if we reduce everything, Jan Smuts, but Einstein actually said it to Jan Smuts also, and he said to him that he believes holistic framework of mind, and we see regenerative agriculture is also called holistic management. So there is something to it, but I just don't want. What worries me is a bit of this. We see Greta Thunberg going around the world scaring the living hell out of children. I don't think that type of talk, it should work, should be worth it. I think what needs to happen is that sensible adults should sit down and they say, okay, these are the problems we face, and then we need to solve them rationally and through science and technology. Yeah.
So in principle, I agree with you. I mean, I have a lifetime devoted to rationalism, but I have to say that when I look at how change actually occurs in the world and how decisions get made, rationalism is actually quite a small fraction of that discussion. In all honesty, it's an indispensable fraction. Obviously, I believe that, or I wouldn't continue doing what I do. But many of these decisions, the way we change behaviors in particular, is actually through emotion, not through calculation and rational.
Right, fair enough. There is a, but I don't like being frightening people, because irrational decisions, we've seen in the past, how people with good intentions can make bad mistakes by just being irrationally and panicking. And I would even say during this pandemic, we saw it in some countries, even including South Africa.
I mean, another learning that we have over the last number of years through all kinds of issues is, unless you offer people hope, then it's a perfectly rational thing to do, just to throw a big party and go out with a bang. So you kind of have to cling, no matter how slim the evidence is, to a future which has elements of hope in it.
Okay.
And
So I've got a final question for you on YouTube, and then I think we're going to end. And once again, thank you, Prof. And it's a bit of a question in lines to what Andrew is saying, but it's sort of trying to sum it up. It says, don't you think many scientists who disagree with you on the climate change narrative are discouraged from speaking out? So aren't they being stigmatized? And I guess my answer to that would be, I would say anyone needs to speak out on this thing, and the good arguments and the good science will eventually win out. But I understand that sometimes it is frustrating. To give Richard Dawkins' example, he says, you're trying to explain the Roman Empire, and then somebody denies that Rome exists at all. So what is your view on treating climate deniers or skeptics, or just people who are lukewarmers, as heretics?
So I think that we have a mechanism for dealing with this. So imagine you've got some life-threatening illness, okay, and you go to the doc and he says, I think that you should drink this snake oil or whatever, and you'll be cured. You're going to go and ask, for a bunch of diversity of opinions. You're going to go and ask for second or third opinions, and then you're going to have some rational process of sorting those out from one another. And that's exactly what we do around these big global problems. It's called the Intergovernmental Panel on Climate Change. It consists of thousands of experts, not only scientists, incidentally, people from economics and psychology and development theory, even these days, philosophers and faith-based people and whatnot. And you put all of this stuff together and you discuss it, you lay it out, okay, the pros and the cons and the evidence in support, and then you say, what do we agree with, what don't we agree with, okay, and what is our kind of, best projection of the future. That's the mechanism we have. Can you imagine designing, if you designed a way to deal with this problem, would it in fact be any different from that?
I would, yes, I have a different solution, but okay, I mean, it's not too sensible. My view always has been with governmental science departments, it's because I'm very skeptical of governments dealing with most issues, but I do find that the scientists who work for governments tend to be more accurate than most people want to make it out, right? Even the COVID, all the conclusions I make, I draw from WHO data. And even though I disagree with the handling. So I do think that we need to have a middle point of the data and where it's collected, etc. But I do believe, though, that a centralized authority is not always the best way to deal with problems, and it has to be on a decentralized basis. And I'm a bit skeptical of international organizations because they tend to select people that tend to be dogmatic and agree with them. I'm not saying it's happening with their panel, but if you look at the UN, for example, you find buddies and friends of friends, and even though they have different colors, they share the same opinions, right?
So, I mean, I have deep experience with these, and not only the IPCC, the Biodiversity One, and I have, for instance, led scientific panels in South Africa on contentious issues such as fracking in the Karoo or how to handle elephant culling and that sort of stuff. And what you do is you build as broad a church as you can. You get people from you'll never frack to the people who think that's the best possible solution. And you bring them in and you work through the evidence, and actually it leads to you're not actually trying to force a consensus, because on some of these things, they're values-based, and so you can't reach a consensus. But what you do is you draw out the range of legitimate options, okay? And that's kind of the way forward on these things.
Okay, well, I think that's a very important point, is that in all of it, in Western values, or even South Africa, it's not really a Western country, you have to do these things democratically. It doesn't matter what your conclusion is, and you need to find consensus. And I do believe ultimately that the good arguments and the good things win out. So, Prof, I think we're going to end here. Thank you very much for joining us, and I'm going to invite you again, but it'll be a conversation between you and me, so we don't... Because it's important to have debate and discussions. As I say, Andrew gave his side of the story on Monday, and if people want to look at what he said, go and look at it and come back and look at what the Prof said, and I'll invite both of them again to talk personally to me, and we can deal with this thing. Thank you very much, Prof. I really appreciate it.
All right. Cheers. Thanks, everyone.
Take care.
Bye-bye.